Welcome back to Aerominds Training Centre, where we simplify complex aviation topics for CPL students like you. In our previous videos, we've already broken down VOR, your bearing provider, and ILS, the system that guides you safely down to the runway. Today, we are diving into a third essential navigation aid, DME, or distance measuring equipment, the tool that tells you how far you are from a ground station, be it a VOR or an ILS. Whether you are on a DME arc, flying a non-precision approach, or just trying to get an accurate fix, understanding DME is absolutely essential. So let's break it down, from how it works to how pilots use it in real operations. Let's begin with an overview of DME distance measuring equipment. DME is a secondary radar system used in aviation to measure the slant range, that's the straight line distance, from an aircraft to a DME ground station. It operates in the UHF band, specifically between 962 and 1213 MHz, with 1 MHz spacing. This setup provides 252 channels, and there's always a frequency difference of ±63 MHz between the interrogation signal sent by the aircraft and the transponder reply from the ground station. Now, there are two key setups you should know. Military aircraft typically use TACAN, that's Tactical Air Navigation, which provides both range and bearing to the pilot. Civil aircraft, on the other hand, usually use VOR or DME, which are often co-located. Pilots tune the paired VHF frequency to get range information from either a civil DME or a military TACAN station. Also, DME is frequency paired with the ILS localizer. In this case, the range information is zero reference to the runway threshold, meaning when you are overhead the runway, the DME reads 0. Pilots simply select the ILS frequency to receive DME distance. That's your introduction to DME, now let's see how it's actually used in flight. So now that we know what DME is, let's talk about how pilots actually use it in flight. First, DME provides a very accurate measurement of slant range between the aircraft and the ground station. This is crucial for navigation and approach procedures. When the aircraft is equipped with an appropriate onboard computer, it can even take the change in slant range over time and convert it into useful information like ground speed and elapsed time to or from the station. DME also allows for more precise flying of holding patterns and DME arcs, especially during instrument procedures where position awareness is key. In non-precision approaches, such as VOR or locator-only letdowns, DME helps with range and height cross-checks, improving safety and accuracy without full ILS capability. And finally, during ILS or DME procedures, DME gives pilots accurate range to the runway threshold, and helps determine expected altitude at certain distances, making approaches both more predictable and safer. In short, DME is more than just a distance tool, it's a critical part of instrument flying. Now let's understand the principle behind how DME works. DME operates using the pulse technique. It's a secondary radar system that calculates slant range by measuring the time delay between signals. Here's how it works. The aircraft is equipped with an interrogator, which sends out a stream of omnidirectional pulses on a specific carrier frequency. At the same time, the interrogator's receiver begins what's called a range search, waiting for a reply. The ground station, which has a transponder, receives these interrogation pulses and, after a fixed delay of 50 microseconds, it replies with a pulse signal. But here's the catch, the reply is sent on a frequency that is ±63 MHz different from the interrogation frequency. This separation prevents interference between the outgoing and incoming signals. The system then measures the time difference between when the interrogation was sent and when the reply was received. This time delay is used to electrically calculate the range. Modern DME systems are quite accurate, typically within ±0.2 nautical miles. Also, DME is built to handle multiple aircraft simultaneously. In fact, up to 100 aircraft can interrogate the same DME station at the same time without causing confusion. Lastly, each interrogation pulse is 3.5 microseconds wide, which corresponds to a physical length of approximately 1050 meters. So in essence, DME works by timing a two-way signal and converting that into a precise distance. Let's now look at how station identification and signal processing work in DME. Every DME station transmits a 3-letter call sign, usually in Morse code, once every 30 seconds. This helps pilots identify the DME station they're tuned into. Now keep in mind, DME signals obey the line of sight rule. So the higher the aircraft, and the higher the DME ground station, the greater the reception range. The aircraft's DME receiver includes a 10-second memory circuit, which allows the system to continue displaying the last valid range even if the signal drops temporarily. To prevent frequency interference, each DME station has a designated operational coverage, or DOC. This defines a safe operating zone in terms of both range and height, and ensures the station won't interfere with others on the same frequency. Now here's how the system locks on to the DME signal. At the start of a range search, the aircraft's interrogator transmits at 150 pulse pairs, continuing up to 15,000 pulse pairs in total. If there's still no lock-on after that, the system reduces the pulse rate to 60 pps, and continues until a successful lock is achieved. Once the aircraft has locked onto the signal, the system switches to a random pulse rate between 25 and 30 pps. Now you might wonder, with so many aircraft using the same DME, how does the system avoid confusion? Here's how. The aircraft and DME transponder use unique pulse patterns. The receiver on the ground sees all the pulse pair requests coming in from many aircraft. But it only replies to those that match the unique pattern sent by our aircraft. Finally, let's look at channel frequencies. In the low band, aircraft transmits on 1025 to 1087 MHz. Ground replies on 962 to 1024 MHz. This is called a Y channel. In the high band, aircraft transmits on 1088 to 1150 MHz. Ground replies on 1151 to 1213 MHz. This is known as an X channel. So overall, we get 63 X channels and 63 Y channels, and each DME channel is defined by this unique pairing of aircraft and ground station frequencies. Let's now understand how accurate DME is, and how far its range extends. According to International Civil Aviation Standards, DME must be accurate to ± 0.25 nautical miles, or ± 1.25% of the aircraft's actual range, 95% of the time. That's a pretty tight tolerance for operational use. Now what about range? DME can work at distances of up to 200 nautical miles, depending on aircraft altitude and the location of the DME ground station. To estimate the maximum theoretical range, we use the VHF range formula, 1.25 multiplied by √HT plus √HR, where HT is the height of the aircraft, in feet, and HR is the height of the DME station. DME measures slant range, not horizontal range. This means when the aircraft is directly overhead the DME station, the equipment shows the aircraft's height in nautical miles, because your horizontal distance is 0, but you still have vertical separation. Now about ground speed, the aircraft's DME system computes ground speed from the rate of change of slant range. But there's a catch. The closer and higher the aircraft is to the DME station, the more the system will underread the actual ground speed. And if the aircraft is circling the DME at a constant distance, the indicated ground speed will be 0 knots, because there's no change in slant range. So while DME gives us great accuracy and range, it's essential to understand how geometry affects the readings, especially during approaches and holding patterns. Next, let's talk about DME beacon saturation. What happens when too many aircraft try to use the same DME station? A DME beacon can handle signals from up to 100 aircraft simultaneously. Beyond that, the system becomes saturated, and some aircraft may not receive accurate replies. Here's why. The ground-based DME transponder continuously transmits around 2700 pulse pairs, and it does this whether or not it's being triggered by aircraft. Now each aircraft's DME interrogator sends requests at about 25 to 30 pulse pairs once lock-on is achieved. If we take the average, let's say 27 pps per aircraft, then 2700 divided 27 equals 100 aircraft. So that's the maximum number of aircraft a DME beacon can reliably handle at once. Beyond that number, the system simply can't keep up, and some aircraft may experience delayed lock-ons or interrupted replies. That's why DME beacon saturation is an important performance limitation, especially in busy airspace or near major airports. Let's finish with an important concept, self-triggering in DME systems. Imagine this, if both the aircraft and ground station were using the same frequency for transmitting and receiving, there would be a major problem. Here's what happens. The ground transponder sends out its reply pulses, but some of those signals get reflected off nearby objects, like buildings, hangars, or terrain. These reflected signals might bounce back to the transponder itself, and the transponder could mistakenly think they came from an aircraft. It then replies again, generating a false range, not to the aircraft, but to the reflecting object. This whole phenomenon is called self-triggering. It creates false readings and incorrect distance measurements. That's exactly why, in secondary radar systems like DME, the transmission and reception always occur on separate frequencies, separated by ±63 MHz. This design effectively eliminates the risk of self-triggering and keeps the system reliable. So that wraps up our look at how DME works, from its core principle to the advanced technical limitations like beacon saturation and self-triggering. From understanding slant range to exploring real-world uses, accuracy, and even beacon saturation, we hope this video made DME simple and crystal clear for your CPL ground studies. And for daily aviation posts, DGCA updates, and crash course info, follow us on Instagram at Aerominds Training Centre. Aerominds is here to help you ace your CPL ground subjects, smarter, faster, and 100% result guaranteed. See you in the next video. Until then, keep learning, keep flying.